Hey, Science 20s, you're back from the break, and it's time to talk about collisions. This is the second part of physics for Science 20, and it goes pretty quick. We'll be done this week, maybe even by Thursday. Collisions involve two things. Newton's laws. Newton's first law says an object in motion tends to stay in motion. Now, I'm put a little asterisk there because we're going to talk, there's a second part to that. An object will always accelerate in the direction of the net force. Okay, now let's talk about this first one just a little bit. You've probably heard that before, right? An object in motion tends to stay in motion. There's a second part of that a lot of people miss, and that's unless acted on by an outside force. One of my favorite video games is Mass Effect. And if you don't know what Mass Effect is a space game, like a science fiction game set far in the future when humans have found ways to get from one star system to another using these things called mass relays. Now, that's neither here nor there, but there's a lot of really good humor in these games. And my favorite part was your character could just wander around, and when you would get by people, they would be having conversations, and you could eavesdrop on their conversations. And there's this one part, I was next to this military captain, because they still have armies in outer space, and they have spaceships. And this army captain was just yelling at these two Marines, and the Marines were standing, they were very sad. And this guy was just shouting at them, and he was telling them about Newton's laws, because these two guys in a spaceship, there's a very bad drawing of a spaceship, shot like a space bullet, like a giant round. And he was telling them, do you know what Newton's first law is, maggots? And they're like, no, yes, sir. Because in space, if you shot a bullet randomly at nothing, and you had the ability to shoot something very quickly, that bullet would travel in a straight line. Maybe for millions or billions of years if it was going fast enough. Like, especially if you're out beyond the gravitational pull of the Earth. And that's what he was telling these guys is like a million years from now, you've lost track of this bullet. It could run into somebody else just minding their own business a million years from now. Like, imagine if you were just like, you're a spaceship guy and you're on your way to get groceries from Mars, and some bullet that was shot a million years ago blew up your spacecraft. Now, of course, there's other things in space that would affect that, like gravity of planets and micro asteroids and things like that would probably slow it down, but it was very funny. Okay, nope. So the first formula we're going to look at with collisions is the force formula. Force is mass times acceleration. And acceleration is the change in speed over time. So this is the simplified formula. This is the more complicated formula. Remember that from the previous unit? So you may have to use the simple formula if you're given acceleration, and you may have to use the more complicated formula if you're not. Okay, let's just try a few of these. What is the force behind a 250 kilogram boulder speeding down a hill at 5 meters per second squared? Okay, now we know the mass is 250 kilograms. We know the acceleration is 5 meters per second squared. So we can use the easy formula, and we can just throw the numbers in there. 250 kilograms times 5 meters per second squared. Right? So that's basically just 250 times 5, and that gives us 1,250 newtons. Now, we probably, as always, I'm going to tell you we need proper sig figs, and there's 3 sig figs that we need. That's 1.25 times 10 to the, moving it back, 1, 2, 3 newtons. A newton is a fancy way to say, kilogram meters per second squared. All right, next one. If a 1,200 kilogram SUV is decelerating at 6.5 meters per second, what is the force? Okay, again, very simple. Force is equal to mass times acceleration. I'm just going to put those in there. We don't need to spend time writing all this down. And because we have deceleration, there's a tricky thing we're going to add. Deceleration is a negative acceleration. Oh, you can have a negative force because force can go in any direction. It can even be stored deep inside of you, that when some black-haired, greasy-looking hipster guy in a mask starts talking to you, it awakens, and you can start moving lightsabers and things like that. That was a Kylo Ren joke. Okay, anyways, that gets us to 7,800 newtons, negative. And proper sig figs, it looks like we need 3 sig figs. So 7.80 times 10 to the 1, 2, 3 newtons. Okay, pretty simple, just timesing the two together. All right, moving on. All right. We already talked about this. Now, in the context of forces, there are things in vehicles that use force, but to keep you safe. 2 of those are airbags and crumple zones in cars. Back in the day, cars were made of good old Detroit steel, and they didn't have airbags. And even though your grandparents will want to tell you that cars were way safer back in the day, they weren't. Yes, there were way less people killed in car collisions, but that's a bad example because there are also a tiny fraction of the number of drivers that there are today. Those old cars weren't great at protecting the occupants from force of collision. The crumple zone slows down the deceleration, and airbags slow down the deceleration. Okay. I'll have a link to these videos. So let's take a look at what happens if you are in a really bad collision. Now, if anybody has been in one and this is kind of painful to talk about, I apologize, but Science 20 grounds force in something like you can all wrap your head around. It's like a collision in nature. Okay. All right. So let's say your car's 1,500 kilograms and it's traveling at 50 kilometers an hour and it hits a light pole. It comes to a complete stop in 0.5 seconds. What's the force? Now, we don't have acceleration here, so we are going to use the advanced formula. Force is equal to mass times the change in velocity over time. Okay. Now, let's just write down what we know to make this a little bit easier to see as we do. It says it comes to a complete stop, so that's a velocity of 0. Before you hit the tree, you are going only 50 kilometers an hour, which doesn't seem very fast, but that's a deadly speed for war collisions, 14 meters per second. And because we came to a very quick stop, it's probably even less than half a second, maybe like 0.2 of a second, but we'll just use 0.5 of a second. All right, let's throw everything we know in there. 1,500 kilograms. VF is 0. VI is 14. Time is 0.5. Okay, so how do we do the math on our calculator so we don't get all screwed up? I would do the stuff in the brackets first. So I'd go 14, because 0 minus 14 is 14, but remember that's negative, because 0 minus 14 is negative 14, divided by 0.5. Okay, that gives me 28, and then I'm going to times that by 1,500. Okay, I get a really, really big number, and remember it's going to be negative because this is deceleration. 42,000 newtons. Okay. Now, if you had your seatbelt on, some of that force would be taken by the seatbelt. If you didn't have your seatbelt on, that force would be impacted to you, the occupant of the vehicle. Now, let's take a look at the next question. Okay. Consider you had crumple zones. So same math, except the stop occurs over longer periods of time because you've slowed down the deceleration of the car. The crumple zones take time to crumple. The airbag cushions your body to a stop. What's the new force? Okay, so force is equal to mass of velocity final minus velocity initial over change in time. Okay, now the mass of the car is 1,500 kilograms, same car. Okay, we're coming to a complete stop. The velocity initial, we're traveling the same speed, 14 meters per second. But the time now is 1.5 seconds. Now, anytime the bottom of a fraction gets bigger, the division is going to be a smaller number. So when I go 14 divided by 1.5, I get 9.333 repeating. I'm going to times that by 1,500. Whoop, too many zeros. I'm going to times that by 1,500. Okay, times that by 1,500. And I get 14,000 newtons. So compared to the previous collision where we had 42,000 newtons, that was a significant amount difference. Now, I can almost guarantee you that if you collided with the tree, you're probably stopping way faster than that. So the force is going to go up even more. And as well, the faster you go before a collision, the bigger the force is as well, because it's just math. Okay. And one of the things that creates this force is called inertia. Inertia is the resistance of an object to move based on its mass. So if something has more mass, it's more difficult to change its motion. If I went back to this question, and we'll talk about inertia tomorrow a little bit more. If we go back to this question, the force impacted would be even more if the mass went up. So as a way to finish up this little math exercise, force is dependent on speed, it's dependent on mass, and it's dependent on time. So all three of those things go with vehicle safety and driving. You can't really protect yourself from mass. The weight of your car is the weight of the car, and unfortunately anybody that hits you, you're at the mercy of whatever their car weighs. But you are at the mercy of how fast you're going and how quickly you decelerate. How quickly you decelerate is based on all of those safety features in a vehicle. How fast you're going is based on road conditions, right? I don't know if you've ever tried to drive really quickly in a snowstorm. That's kind of stupid. But if it's a nice clean day and you're wide awake, you can probably bomb along at a pretty good speed on Highway 2. In fact, if you're not going really quick, you're going to get run over. Okay, so that's the lesson on force today. I have a really quick Google form, kind of like a quiz I'd like you guys to try that goes with this. Don't forget the question set is due today from before the break.